Bismillahirrahmanirrahim. I welcome you to the 9th lecture of the series of lectures on advanced computer architecture. Today, my focus of discussion will be the design of multi-cycle data path and its control unit. I will also try to give you an introduction on the pipeline architecture if some time is available. So first I will give you a brief review of what we discussed last time. Last time I talked about the design of single cycle data path for some basic instructions such as the register type, add and subtract, immediate instructions, memory reference instructions, that is the load and store instruction, and control instruction, that is the jump or branch instruction. In this discussion, we studied how different types of instructions are being executed and what is the information flow from one part of the system or the data path to the other part of the data path. Then we also talked about the use of different parts of this data path design. Here we observed that the memory is used only twice at two different times. First, when the instruction is fetched, and second, when some data is to be either stored into the memory or it is to be read from the memory and loaded into a register. So this means that, and this is why we divided the memory into two parts as the instruction memory and the data memory. Whereas we also noticed that in order to calculate the address for the next instruction, during the instruction fetch cycle, we used two adder units, whereas the adder unit available in the ALU is used only when either an odd type instruction is to be executed or the operand of immediate data is to be added to find out the address for load type or stored instructions. So this means that the adders available in the instruction fetch unit are not used for all the times, rather they are used only for a fraction of time. Similarly, we also found that the ALU is not effectively used for all time, and most of the component remains idle for part of the execution during the flow of data from one register to another register or in the data path. So as a conclusion, we can say that we can improve the design by reducing the hardware, but I think in this particular case we will use or need some extra control, and this is possible by using another approach which I am going to discuss in more details today, that is the multi-cycle approach. As you observed that in a single cycle approach, we maintain the instruction cycle to be equal to the total time required to fetch and completely execute an instruction, where the execute includes instruction decode, the calculation of the result, or determination of the address in the case of load or store instruction, and also to either load the data into the register or write the results into the destination register, this operation is known as the write back operation. And similarly, to perform the memory operation if it is a memory reference instruction. So this shows that this total time of one instruction cycle can be divided into subsections, and in each subsection, which is known as again a cycle, but this cycle is of smaller duration as compared to duration of the cycle used in single cycle data path design. For example, if the single cycle data path design requires a cycle length of 5 microseconds, which is determined based on the total time required to fetch, decode, execute, perform memory operation, and the write back operation. As this total time can be divided into smaller steps, and each sub operation can be completed in one small step. And this type of technique is known as the multi-cycle approach. So this shows that if we are ready to use the multi-cycle approach, we can have the cycle length equal to 1 microsecond, which is the longest time required to complete one step of all the 5 operations, or one of the 5 operations are sub-operations which are required to completely fetch and execute an instruction. As we know that the memory read or memory write, that is the memory reference, that usually take the longest time. The ALU time is equal to, or the execute time is equal to the time required to completely perform an ALU operation. Similarly, the instruction fetch, it involves memory read because we have to read the instruction code from the memory. Now, in all these different types of steps which we have to perform during the execution of an instruction, the memory operation is usually the longest. Therefore, the step size for multi-cycle operation is determined based on the time required to read either data from the instruction memory, that is during the instruction fetch cycle, or to read the data from the data memory in case of load instruction, or to write data into the memory during the store instruction. So, considering these facts, let us assume that we divide the complete cycle of a single cycle data path, which I said in the beginning, say is equal to 5 microseconds. We can divide it into 5 steps, each of 1 microsecond. So this means that now we need a clock where the time period of the clock is 1 microsecond as compared to the clock required for single cycle data path, which we assumed to be equal to 5 microseconds. So considering this, we can now see that we can perform different operations in different clock cycles. For example, during the first clock cycle, we can perform the instruction fetch. During the second clock cycle, we can perform instruction decode operation and the register read operation. Similarly, during the third clock cycle, we can perform the execute, which depends upon type of instruction, and it also determines the next step. If it is a load or store instruction, the execute is the address calculation, and the next step will be the memory read or memory write operation. Whereas if it is a register type instruction, the memory operation is skipped and the write back operation is being performed. So in this whole process, we can see that the load instruction is one which takes all the 5 steps. So it takes longest time in order to execute. And this is the instruction which actually determines the size of the clock in case of single cycle data path design, which we said in the beginning to be equal to 5 microseconds. So considering this, we can now look into this diagram and can see how effectively we are using the time available in a single cycle data path as compared to the multi-cycle data path, and then how we can improve upon the performance of the system in terms of time required to execute an instruction or a program which may be consisting of different types of instructions. As I have just said, that in case of multi-cycle data path design, some instructions may be completely fetched and executed in 3 clock cycles, like the jump or branch instruction. Some other instructions may be completed in 4 clock cycles or 4 steps, like the register type instructions or the store instruction, whereas the load instruction, it requires 5 clock cycles to complete the operation. Now, for this purpose, in order to evaluate the performance of a single cycle data path versus the multi-cycle data path, let us consider an example program. In this small program segment, we may assume that our first instruction is a load instruction, the second instruction is a store instruction, and the third instruction is, say, a register type add instruction. So if this program segment is to be executed by using single cycle data path, then it takes 3 clock cycles to completely execute this small program segment. Therefore, as we assumed that each clock cycle of a single cycle data path in our example is 5 microseconds, therefore the program will take total 15 microseconds to be executed. Whereas in case of multi-cycle data path design, the load instructions can be executed in 5 steps. Store instruction is executed in 4 steps, and register type add instruction is executed in 4 steps. Therefore, it requires total 13 microseconds to completely execute this small program. Here, if you look into this diagram, you can see that during the execution of the load instruction through the single cycle data path, no time wastage is there, whereas in case of the store instruction, the single cycle data path completes the operation in approximately 4 microseconds because it does not involve any memory read operation. Rather, it is a simple memory write operation, and there is no write back operation involved in this. Therefore, the last part of this single cycle, that is wasted, or the system gets waiting for the next tick of the clock. Similarly, in case of the load instruction, the instruction is completed in first 4 microseconds, and the system remains waiting for the tick of the clock for 1 microsecond, and in this way, this time goes wasted. So therefore, if we look into this whole scenario, we can say that multi-cycle data path is faster. In the case of this example program, it is faster by 1.24 times, that is 24% faster as compared to the single cycle data path. So this shows that the single cycle data path, there is some time wastage, and which can be saved if we are ready to use multi-cycle data path. Now I will talk about what are the constraints of the design of a multi-cycle data path. For this purpose, let us refer to this diagram, which is giving a high-level view of a multi-cycle data path design. Here, a shared memory is used as the instruction fetch and data read or write are performed in different cycles. Here you can see that a single ALU is shared among the instruction fetch, execute, arithmetic, and logic instruction, and address calculation in different cycles. The use of shared functional unit ALU, it requires additional multiplexers or widening of multiplexers in order to accept data from different sections of the data path. New temporary registers, instruction register, data memory operand registers A and B, and an ALU output register are included to hold the information to use in later cycle. For example, memory read in cycle 4 is written in cycle 5 for the load instruction. Operand register A and B read in cycle 2 may be used in cycle 3 or 4, and similarly for some other types of instructions we may look into this for this particular purpose. Now, considering this, let us consider the next detailed diagram of the multi-cycle data path. Here you can see that I have used different colors in order to show different sections which are being activated when different types of instructions are being executed. For this purpose, you can see that here we have effectively used the hardware, and the overall hardware have been minimized. Similarly, you can also see that in this particular data path, we are using a common memory unit which holds either the instruction code or the data or both simultaneously in one memory, no doubt at different address places and different parts. This concept is being used in almost all the Intel family design of 80x86 microprocessor design, where there is one memory unit, and this one memory unit is being shared for instruction, for stack operations, for data, and some extra information to be stored. And accordingly, in case of Intel architecture, these sections of the memory are identified by the contents of a register in the microprocessor known as the data segment register, the code segment register, the extra segment register, and the stack segment register. However, considering this particular design of multi-cycle over here, you can see that here we are showing with the help of yellow path over here that in cycle 1, which is the instruction fetch cycle, firstly, the multiplexer MUX-1, it selects input, which is its select input I or D, it is made equal to 0, and the program counter is connected to the memory read address input, which is shown over here as R address RADR. Instruction is fetched from the memory at the data output. Here, as I have just mentioned, that there is only one memory unit, so there is only one output point. The instruction code is available at the D output, and this code is stored in the instruction register. at this point. Secondly, the select input ALU select A to multiplexer 3 is made equal to 0. ALU select B to multiplexer 5 is made equal to 0, 0. Here you can notice that the multiplexer MUX5 is a 4:1 multiplexer. Therefore, 2-bit code is required at its select input. And for this particular purpose, this select input is equal to 0, 0. As you can see from the diagram, the 4 values which may be provided to the ALU as the second operand are: the topmost value is equal to 4, which is used to find out the next address in the program counter. If you recall from our previous discussion, on the completion of the fetch of an instruction, the program counter is to be incremented by 4. The other data values which are available at the second, third, and fourth input of the multiplexers, I will talk accordingly how it is going to be used in the further next cycles. So over here, as you can see, when the select input has been made equal to 0, 0 at the multiplexer 5, then PCSRC, which is the program counter source input of the multiplexer 2, is made equal to 0, and the control signal PC write, which is PCWR, is asserted to load a value, updated value of the program counter, which is equal to PC plus 4, to the program counter as address of the next instruction. Now let us see what is happening during the clock cycle 2. The clock cycle 2 is basically used for instruction decode. However, as you know that as we discussed in the single cycle case also, the instruction decode takes minimum time, which is in fact a decoder, which is done with the help of a decoder circuit, which is a combinational logic circuit, and usually the time required is equal to the propagation delay of gates used in the instruction encoder. So considering this thing, and in order to efficiently use the second clock cycle, the registers are also read during the second half of the clock cycle. These two registers, which are identified by the RS and RT in the instruction word, by the address RS and RT, they are read in anticipation of whether they are to be used for R-type instruction or they are to be used for some other type of instruction. Sometimes they may be used, sometimes they will be ignored. For example, in case of R-type instructions, these values are the operand values, and they are made available at the input B or in the B register, which we have said that an additional register has been added over here. Whereas the function of clock cycle 2 is shown. Here you can see that firstly, the instruction is decoded. The RS, RT, RD, and immediate 16th field of the instruction word are made available on the respective lines. Secondly, the registers at RS and RT are read at buses A and B respectively, and they are stored in the respective registers, temporary registers A and B. Here you can see from this slide the function performed during cycle 3, which is the execute cycle. Here you can see that the select inputs ALU select A and ALU select B to the multiplexer 3 and multiplexer 4 respectively for the instruction in hand available at the ALU output ALU operation input to the ALU control unit, we can see over here that the functions for the different instructions are different in case of this cycle. For example, here first let us consider the register type instruction. In case of the register type instructions, as you can see here, the ALU select is made equal to 1, ALU select B is made equal to 0, 1, ALU select A is equal to 1 and B is equal to 0, 1 to connect the bus A and bus B to ALU to perform the operation. The next, let us consider what's happened in case of immediate types of instructions. Here you can see that ALU select A is made equal to 1 and ALU select B is made equal to 1, 1 to connect the bus A and sign extended immediate 16 to ALU to perform the operation on immediate data. The ALU output is kept in ALU out register as result of ALU operation execution in case of I-type operation and as memory address in case of memory instruction load are stored. Whereas in case of J-type instructions, the data path performs the operations after evaluating the conditions. As you can see from this diagram over here, that the first of all condition test is performed, and in order to perform the condition test, ALU select A is made equal to 1 and ALU select B is made equal to 0, and ALU operation at this time supplied is the subtract operation, because condition is always evaluated by subtracting one operand from the other, and if the result is equal to 0, then the required new address is calculated, and if the result is not equal to 0, then no change in the contents of the program counter is being performed. So over here, I would like to tell you one thing, that during the execute cycle, in the first step, the condition is being evaluated. And at the same time, if the condition is successful, then the program counter is to be updated by adding the sign extended value available in the immediate field, and after shifting it 2 bits to the left. So this shift of 2 bits to the left, as I discussed earlier, even in case of a single cycle data path, it is performed in order to align the address at the 4-byte position, because our this sample data path is designed for instruction words of 4 byte in length. So over here you can see that if the condition is satisfied, then ALU select A is made equal to 0, ALU select B is made equal to 1, 0, where with the help of this 1, 0, we pass on the value of immediate sign extended with shift to the left, and the signal branch right, that is BRWR, that is asserted, and the program counter source of the multiplexer 2 is made equal to 1 to pass the target address to the program counter, which is shown here. Now let us have a look onto the 4th cycle. During the 4th cycle, as we mentioned earlier, the 4th cycle is the memory operation cycle, and this cycle is used only in case of load and store instruction. However, it has got different types of control signals which are to be applied for the load instruction, and different types of control signals are to be applied for the store instruction. So let us first of all consider the load instruction. Here you can see that I or D is made equal to 1 to pass the ALU out register as register address or the read address input to the memory to read the data at the data out. Whereas in case of store instruction, memory write is asserted as the ALU out register output is wired to write ADR, which means that write address input, which is again shown here, and bus B of the register file is wired to data in, which is the data in to the data memory. Because in case of store instruction, the data write is performed, and in case of load instruction, data read is performed during the 4th clock cycle. Whereas the 5th clock cycle, which is known as the write back clock cycle, this cycle is used for different types of instructions, and for the register type of instructions during this cycle, the result available in ALU out is written into the destination register. And for this purpose, as you can see from this diagram, register destination of the multiplexer 4 is made equal to 1 to select RD as the destination address. The memory to register is made equal to 0 to connect ALU out to the write bus, and register write signal is asserted. Whereas in case of I-type instruction, in the case of immediate data type instruction, the immediate data value which has been extended and the result is available in the output register, but in this particular case, the result is again written into the destination register RW, and the signal asserted R, as you can see from here, the register destination to multiplexer 4 is made equal to 0 in this case to select RT instead of RD. This, if you recall from our earlier discussion, when we were talking about the instruction word format, there we said that register RT and RD, they are interchangeably used as the destination register for certain instruction. Particularly, a register address given in field RD in case of R-type instructions is the destination register, and the register address field given in RT, that defines the destination register in case of immediate data type instruction. The other operation which is being carried out during this clock cycle is the load instruction, because in the load instruction, whatsoever is the data which has been read from the data memory, that is to be written into the register, and this cycle is known as the write back cycle. So basically I have used this word as cycle 1, cycle 2, cycle 3, etc. Just for making it easy to understand the sequence in which different operations are to be performed. But in principle, we can say that the cycles should be named as the instruction fetch cycle, instruction decode and register read cycle, execute cycle, memory reference cycle, and the write back cycle. Whereas the write back cycle in case of the register type instruction is the 4th cycle. Similarly, in case of the load instruction, it is the 5th cycle. Whereas for different instructions, some other cycles has to be missed. This will be clear to you when I will be talking about the design of the control unit. for the multi-cycle data path. So with this much discussion onto the design requirements of multi-cycle data path, we will have a look into the design of the control path for the multi-cycle design. As we have observed in our discussion about the design of multi-cycle architecture, we have noticed that the control unit has to operate in a particular sequence. For example, depending upon the type of instructions, the different sequences are to be followed after the instruction decode. So this means that during the first two parts, that is the instruction fetch cycle and instruction decode and register read cycle, function is common, but the next step may be different depending upon what is the result of the instruction decode. So this means that the control unit which is to be used in order to generate the signals to activate different parts of the multi-cycle data path, that must be a finite state machine, and this finite state machine therefore can be designed by using the principles of the design of a finite state machine, which is also known as the sequential circuit design. Moreover, as the operation of multi-cycle data path has to follow a particular sequence, therefore we can also use another approach which is known as the microprogramming approach in order to generate the control signals to operate a multi-cycle data path. So let us first of all consider the finite state machine based design of the control unit. The first step in the design of the finite state machine based control unit is to draw a sequence diagram. Here, let us consider this sequence diagram shown over here for some subset of the instructions, but this sequence diagram covers all the three types of instructions, that is the register type instructions, I type instructions, and J type instructions. Here, as you can see from this diagram, at the topmost position, the first state is the instruction fetch state. During the instruction fetch state, as you know, two major operations are being performed. That is, the instruction code is read from the memory from the location identified by the program counter, and it is written over here that the contents of the memory from the program counter, they are transferred into the instruction register, and the program counter is incremented by 4 to point to the next instruction. The second state is corresponding to the instruction decode and register read. So instruction is decoded by using a simple decoder. So it is only the decoder which is being activated, but the major operations are the register read operations. So over here, as you can see in this diagram, the contents from the location RS, they are transferred into the temporary register A, and the contents from the location from the register file RT, they are transferred into the temporary register B. The next step very much depends upon what is the result of the instruction decode. And this is why over here you can see that at the next step there can be one of 5 possible next states. If it is an R-type instruction, the next state is one where the required operation is performed onto the data, and it is made available in the temporary register S over here. So for the register type operations, the next step is the execute operation. If it is an immediate data type instruction, then one of the operand is extended. If it is a logical instruction, it is extended by adding zeros to the left of the data, and if it is the integer data, then it is the sign bit which is extended. A required operation is performed and it is stored into the S register. Whereas if it is a load instruction, then in this particular case, the sign extended immediate value is added into the contents of the register RT, corresponding to RT or the register whose value has been placed in register B, and this value basically gives the address where from the memory is to be read, and this value is kept in the temporary register S. Whereas if the instruction is a store type instruction, again similar operation is performed as for the load instruction, because this also involves the computation of the address where the data is to be written. Whereas if it is a branch instruction, then in the third step, the branch condition is determined, and this is kept in temporary register S, or for this purpose over here, as we discussed in the data path design, we are using a special simple output, which is the Z output. The next step is, as you can see from this state diagram, the next state always depends upon what is the previous history. That is, what is the present state of the control circuit. For example, in case of R-type instructions, the next step is to write the result back into the required destination register. So the next state is the write back state. And similar is the case with the immediate data type instructions and with the store type instructions. Whereas in case of load instruction, the next step is the memory read operation. Therefore, the next state is the memory read state, which is followed by the write back state. Whereas in case of branch instruction, depending upon what is the value of the condition, whether the condition was satisfied or it was not satisfied, the new address is being calculated, and the complete process is then repeated from the first cycle, which is the instruction fetch cycle. The rest of the procedure to design and implement a state machine is already known to you, because you have already studied these things in your course of logic design or advanced logic design. The second type of control unit design is the sequencer based design, which is also known as microprogramming based design. Microprogrammer based design is one which is using a read-only memory as the main section, which contains the micro operation code for all the instructions. A counter is used to identify the starting point of the micro operations for a particular instruction. And as you can see from this block diagram, whenever we know the instruction code, we can identify this by loading the starting address of a particular instruction into the program counter, and this program counter then gives us all the micro operations which are to be performed, and they are already stored in the ROM which is used with this circuit. However, the complete design of a microprogrammer you have already studied in your basic course of computer architecture. However, those who are not familiar with this one, they are advised to go through this from your reference book, which is by the Hennessy and Peterson, which is Computer Organization and Design. So with this much discussion on to the single cycle and multi-cycle data path and multi-cycle architecture, I conclude our discussion of today over here by saying that the multi-cycle architecture is relatively faster as compared to the single cycle architecture. However, we cannot say that the multi-cycle architecture is an optimum design. Rather, over here, if you carefully analyze, we are not using all parts of the data path efficiently during the execution of any type of instruction. For example, when the instruction fetch operation is performed, rest of the circuit is sitting idle. It is doing nothing. When instruction decode and register read operation is performed, instruction fetch circuit, execute circuit, and the memory reference circuits or the write back circuit, they are not doing anything. Similarly, during the execution phase, the instruction fetch is sitting idle. The instruction decode is sitting idle. Write back is idle. So this shows that different sections are only one part of the whole system is in use, and most of the parts are sitting idle. How we can use the total system efficiently, this we will discuss next time by introducing to you the concept of pipeline architecture, which is the basis of instruction level parallelism. I hope that you have already been introduced with the concept of pipeline architecture in your course of basic course of computer architecture, but I will review the overall design of pipeline architecture, and then we will see what are the constraints in this design, what are the other problems which we can face when we are going to use these type of architecture. So with this much discussion, I stop here today, and till next time, I say you Allah Hafiz.